move on to the next invited talk from Dr. Xingya Li, University of Science and Technology of China.
Okay.
Doctor,
Yeah, I will share my slides.
Yeah, start sharing your presentation, Doctor.
Okay.
We can
So
presentation.
can you see my slide?
Yeah, we can see your slides.
Okay. Thank you for the introduction. Hello everyone.
Start.
Hello everyone. I'm Xingya Li from USDC. So my topic is about microporous framework membranes for ion separation. And here is the outline of my presentation. First of all, I will give a brief introduction about the research background. So our research focuses on the ion separation, which can achieve the extraction of high-value ions or the removal of toxic ions, leading to an energy-efficient separation. So during this process, membranes with high ion flux and selectivity are highly demanded. So for common cations and anions, they have similar sizes and charges, making the precise ion separation a great challenge. So the key point is the construction of fast and selective ion transport channels for membranes. For biological ion channels, such as the proton channel, fluoride, and the sodium ion channels, they have realized fast and selective ion conduction. This is because they have Angstrom pores that close to the ion diameters, posing a confined effect on the ions, as well as the ion selective filters, enabling the specific interaction between ions and the channel wall. So for the microporous frameworks, such as the COFs, they can be used as the building blocks for ion channels, since they have Angstrom pores resembling the biological ion channels. And also they have various functional groups serving as the selective sites for specific ion interaction. So in the second part, I will show how the ion channels are constructed. I will introduce 3 examples. The first one is the fluoride ion channel. Inspired by the biological fluoride ion channel, the artificial fluoride ion channel is prepared by using the MOF UiO66, which will grow into the PT nanochannel. The UiO66 MOFs have 6 angstrom triangular windows for ion sieving and dehydration, and the 11 angstrom cavities can be used for ion transport. In addition, there are selective fluoride binding sites, such as the conium sites and amino and coordinized amino groups. Then we studied the ion transport property in the MOF channel via RV curves. From the curves, we can see the UiO66 MOF channel show a selective fluoride transport over chloride compared to the PT nano channel. And then we figured out the ion transport mechanisms in UiO66 channels via MD simulations. At a dilute concentration, both the fluoride and the chloride ion channels, fluoride ions have tight hydrogen shares in the cavity center. They are partially dehydrated through the window, where at a high fluoride is co-shared by fluoride ions, leading to a loose structure. As a result, a lower energy barrier is required when fluoride ions pass through the window. And from this figure, we can see the fluoride mobility increased obviously with increasing fluoride ion concentration. Considering the unconductivity is related to the ion mobility and the ion concentration, and the selectivity for fluoride over chloride from MD simulations is in line with the experimental value. Then the fluoride selectivity over other anions is also studied. From this figure, we can see the fluoride conductivity is much higher than the other anions. And the selectivity for fluoride over other anions increased with increasing dehydrated ion diameters. The second one is the proton selective channel. Inspired by the biological proton channel, artificial proton channels was prepared by introducing the sulfonic acid groups as the selective filters in the UL66 MOF channels. The high-density sulfonic acid groups in the sub-1 nanometer MOF channels can serve as hopping sites for fast proton transport and simultaneously exclude other cations. And this figure shows the construction of the sulfonate MOF channels. The sulfonate MOF channel is prepared where the in situ groups of amino UL66 in the PT channel and followed by a post-modification with tethered sulfonic acid groups. And from the IV curves, we can see the sulfonate proton channel show a high selectivity for proton over lithium compared to the pristine MOF channel. And the selectivity for fluoride for proton over other monovalent cations is also studied. In the single ion system and binary ion system, we can see the sulfonated MOF channel show a high selectivity for proton over lithium. Then it's the in order to control the proton transport direction, a MOF polymer heterogeneous channel was prepared, where the MOF was grown into one side of the PT channel, or where the control diffusion growth method. And in the nanometer-sized polymer channel, water molecules are confined to disordered clusters, which is adverse for proton transport, where in the one-dimensional sub-1 nanometer MOF channels, water molecules are confined to ordered chains, which can facilitate proton fast transport. And from MD simulations, the ordered water chains formed in the one-dimensional MOF channel with unique molecular configurations, such as the pentagonal water structure and the tetragonal water structure. And from the IV curve, we can see for MOF polymer channel, the currents at positive voltages are much higher than those at the negative voltage, indicating a unidirectional proton conduction. And from the DFT calculations, we can see for the energy barrier for proton transport from the polymer to MOF direction is only half of that for proton transport from the MOF to polymer direction. And in addition, from this figure, we can see among the three MOF channels, the energy barrier for proton transport in mu1 is the lowest. That's why the mu1 PT channel shows the highest proton rectification ratio and conductivity. So previously, we studied the ion transport mechanisms in sub-1 nanometer MOF channels. In this part, some examples of membranes for ion separation will be introduced. So the first one is the polymorph membrane. As we know, MOF particles lack the solution processability, making it difficult to prepare a defect-free MOF membrane. So the polymorph is prepared by using the oligomer to coordinate with metal nodes. And the obtained polymorph is soluble in the solvent EMF. And the membrane can be prepared via the solution casting. So for the as prepared membranes, they show an efficient separation for monovalent cations over divalent cations. Then the spray deposition method was used to prepare the large-scale uniform of complete membranes. Well, a morph layer is deposited onto the porous support, followed by the deposition of a cross-linking layer to immobilize the morph layer. So the membranes we get also show a good separation performance. And this is the COF membranes. So for COFs, they have one-dimensional sub-2 nanometer channels for fast transport. In addition, there are hydrogen bonding sites along the channel, which can be used for unsieving. And this figure shows how the membrane is prepared. So through the interfacial growth, the COF layer was prepared on the AO substrate. And from the characterizations, we can see the pore size of the COF channel is mainly focused on the 1.4 nanometer. And the hydrogen bonding interaction between the amino group and the water molecules. As for the unseparation performance, the COF membrane shows a high monovalent ion flux and a high monovalent divalent unselectivity. Since the hydrated cations are surrounded by water molecules, and from MD simulations, we can see the cation hydrogen bonding energy follows the order, which is potassium lower than sodium, and lower than lithium, and lower than magnesium. And as a result, the ion transport energy barrier follows the same sequence. And the membrane ensures efficient monovalent, divalent, and sieving property. So finally, just a brief summary for my talk. Learning from the biological ion channels, some novel ion channels based on microporous frameworks are prepared and also achieve a high unselectivity and conductivity. And the unselective transport mechanisms in the angstrom-confined channels are reviewed by the MD simulations. Then the microporous framework membranes were prepared and applied for unseparation. So last but not least, great appreciations for my supervisors and my team members for their general help and support. Okay, that's all. Thank you.
Thank you so much for your wonderful speech, Doctor.
Yeah, thank you.
Now the stage is open for questions. We assume there are no questions for you as of now.
Okay.
So, we will write back to you if we receive any questions from the speakers.
Okay, thank you.
Thank you.